When operating in deep water, environmental and weather-related issues such as loop currents and storms, including hurricanes, can force oil field operations to cease and mobile drilling units to move off location. In order for these units to move, the current well must be secured and the working fluid in the riser must be displaced to seawater prior to disconnecting it from the subsea BOP and removing the riser from the sea. In many places, expensive invert emulsion fluids are used while drilling from floating rigs. Current practice is to cease operations and trip out of the well to pick up a mechanical storm packer. This storm packer is run to just below the mud line where it is set to isolate the well. The work string is disconnected from the storm packer and the well is displaced to seawater by pumping conventionally down the work string and up the riser annulus. The displacement rate is increased by also circulating seawater up the riser annulus through the booster line. The fluids still mix, forming a viscous interface. Fluid velocity is not able to effectively remove invert emulsions from the riser wall. By the time the interface reaches the surface, the invert emulsion fluid is sufficiently contaminated to create elevated viscosity due to a shift in the non-aqueous water ratio and potential water wetting of solids. This invert emulsion interface can amount to hundreds of barrels, which require segregation and reconditioning on the rig or at a land-based mud plant. Unfortunately, some rigs have limited pit space and are unable to isolate the contaminated fluid because of the additional volume. If this is the case, either the drilling fluid will have to absorb more seawater, fluid will have to be discharged to the sea, which could be a finable offense, or operations will have to be halted to permit transfer of excess fluid to boats. Each of these options increases cost, invaluable assets, and operating time. In addition to the displacement interface, small amounts of invert emulsion fluid from the riser wall can contaminate the seawater, increasing the amount of time required to remove fluid debris from the riser. This contaminated seawater may need to be isolated and returned to shore for processing or disposal. This can further consume valuable assets and operating time. Once the well is completely displaced, the work string is extracted from the riser and the riser is disconnected from the subsea BOP. The riser is then pulled and stored on the riser deck so that the rig can move off location and out of harm's way. While pulling the riser, some of the residual invert emulsion mud will drain out on the rig floor and riser handling equipment, creating a hazardous work area. Once the riser is stored in sections on the riser deck, more of this drilling fluid collects on the low side of the riser and drains onto the riser deck with movement of the drilling vessel. The Riser Displacement Cleaning Tool, RDCT, is designed to specifically address the limitations and inherent risk with conventional riser displacements. The RDCT is composed of a series of wiper elements to clean the inside of the riser, including the slip joint, an isolation flapper valve, flotation material for neutral buoyancy, and a release mandrel. In addition, a special running tool is used to deploy the RDCT to the subsea wellhead and a retrieval tool that captures the RDCT when it returns to surface. The running tool permits other wellbore safety equipment, storm packers, hang-off tools, to be introduced into the well on the same trip as the RDCT. The running tool is composed of drill pipe and a shroud to protect the RDCT wiping elements while inserting the tool through the riser. The running tool assembly, including the RDCT, can be made up ahead of time and racked in the derrick for quick retrieval when needed. The running tool assembly is inserted into the well. If a storm packer is included in the assembly, it is set below the mud line and the work string is disconnected from it. The annular preventer is closed around the RDCT grasping mandrel. The work string is pulled up to shear the running tool from the RDCT. Drilling fluid can be displaced from below the RDCT with cleaning spacers or seawater, just prior to extracting the work string from the well. As the work string is extracted, the isolation flapper valve closes to provide a mechanical barrier between the two fluids, as well as convert the RDCT into a sealed unit. Once the work string is removed from the riser, the annular preventer is open to release the RDCT. Displacing fluid is pumped down choke and kill lines below the RDCT to push it up the riser. As the RDCT is transported to the surface by this new fluid below, the wipers physically remove any residual drilling fluid film from the riser walls. The wipers are designed to maintain a positive seal along the length of the riser, including the telescoping slip joint. The drilling and displacing fluid remains segregated by the mechanical barrier during the complete displacement process. No viscous fluid interface forms, and fluid contamination is essentially eliminated during this displacement. The RDCT stops at the bell nipple when the seal is broken. The RDCT is then easily retrieved from the riser. When the riser is pulled, there is no mud residue left inside the riser to drain out, either on the rig floor or the riser deck. Comparing the results of a displacement with and without the RDCT makes a marked improvement in minimizing interface. A similar comparison for cleaning the riser shows how the RDCT gives far superior results and eliminates the need for riser cleaning on deck. The RDCT makes a clear difference in the outcome of the riser displacement or cleaning operation. Whether the focus is on safety, the environment, or saving time and money, the RDCT can add value to any riser-focused operation.